9.6, graphs of polar equations. What you should learn: graphs of polar equations by point plotting, using symmetry and zeros as sketching aids, and recognizing special polar graphs. In previous lessons, we graphed rectangular coordinate systems, and we just really learned how to plot in polar. Now let's talk about how to graph in polar. At the very basic, plotting in polar is the same thing as plotting in rectangular. But we're going to make a table. Our x is like our theta. We're going to make a theta, and we're going to have our r. We'll start with 0, and then we'll go pi over 4, pi over 2. Well, let's go 3 pi over 4, pi. Probably want to go for a full circle. I might do more. Maybe let's go 3 pi over 2, and then 2 pi. But we have 4 sine theta. The first one, we're going to go 4 sine of 0. The sine of 0 is right here. That is 1, 0. Sine of 0, I just get 0. Our first point to me is 0, 0. Next one, 4 sine of pi over 4, which is 45. So we're going to get 4 times rad 2 over 2. We all know sine of 45 is rad 2 over 2. We're going to get 2 rad 2, which is about 2.8. Pi over 4 is a pole that looks like this. And we have 3 pi over 4 like this. So we're going to go about 2.8. About pi over 4, we're going to go about 2.8. Look around there. Then we keep on going. Pi over 2. We're going to go 4 sine of pi over 2. Pi over 2 is up here. So that's 0, 1. That's this going to be 4 times 1, which is 4. That point is pi over 2. This pi over 2 is the line right here. We're going to go to 4 right there. Right now our graph kind of looks like it's going. Now it is going to be a curve, but we're going like this. You're not trying to draw that. You're trying to like curve it. So we're trying to do a curve. In polar, it's all curves, not straight lines. 3 pi over 4. We're going to go 4 sine of 3 pi over 4. That's another 45. So it's going to be rad 2 over 2 again. 4 times rad 2 over 2. So it's going to get 2 rad 2. We'll get 2.8. We're going to be at this line, but at 2.8 again. Look around there. And then pi. 4 sine of pi. Pi is over here. Negative 1, 0. We're going to get 0 again. We're going to go back down to there. Our graph looks like this. We want to do curves. I messed up at the end there, but it's basically like a big old circle. Looks like a big old circle right there. And I can keep on going if I wanted to. This one would be 4 sine of 3 pi over 2, which is 4 times negative 1, which is negative 4. Now you're like, oh, negative 4, is that down here? But remember, 3 pi over 2 is over here. But we're going negative. We're going to go back. 1, 2, 3, 4, the same spot. Basically, keep on going around and around in that circle. It's supposed to be a nicer circle with that circle. That's how you pop polar. It's the same thing. If you're not sure what the graph looks like, you just make a table that you're going to do with angles. You plug it in. You get trig values, pull the unit circle, and then you connect it. Just try to connect it with curves instead of lines. Symmetry and zeros. If you notice the picture we just did, it's symmetric about pi over 2. A lot of polar curves have symmetry. Sometimes it's over pi over 2. Sometimes it's over the origin at 0. And sometimes it's on the line here, on the pole. Just be aware of that, and sometimes it can make your life a little easier. If you want, you could test for symmetry. This shows you how to test for symmetry. Honestly, most of the time I just graph. It takes me more time to test for symmetry than it is to actually just deal with the problem. But they can help if you notice it right away. Okay, using symmetry to sketch a polar graph. So we want to sketch this one. Use symmetry to sketch the graph of r equals 3 plus 2 cosine by hand. So again, at first, not knowing anything, we'd go, here's our theta, here's our r. We'll start at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now this is a cosine graph, so anything that's negative will be even. We could use this. If we're looking at symmetry, that would be symmetric over the polar axis, because if I plug in a negative pi, I just get cosine pi. So it should be symmetric over the polar axis. We'll see how it goes. On the first one, just plug it in. Cosine. We'll just do main points here. 1, 0, 0, 1, negative 1, 0, 0, negative 1. So we have 3 plus 2 cosine theta. Cosine, 0. Cosine 0 is 1, so we get 5. Here's my graph again. I have to make it up to 5. Not gonna be pretty. That's 3, 4, 5-ish. Our first point is 0, 5, right there. Pi over 2. So 3 plus 2 times cosine of pi over 2. At pi over 2, we have 0. This is just gonna be 0. That's gonna be 3. At pi over 2, we're gonna be at 3. Right there. Pi. 3 plus 2 cosine of pi. Cosine of pi is negative 1. So we have 2 times negative 1, which is negative 2, but 1. We have pi and 1. That 3 pi over 2. 3 plus 2 times cosine of 3 pi over 2, which is 0. So you get 3. And then 2 pi. 3 plus 2 times cosine of 2 pi. So that's 1. 2 times 1 is 2 plus 3 is 5. To get back to here. So my graph's going to go like this. You can see it is symmetric about this line here. Now, I'd feel better if I had a little more points. I probably should have pi over 4 in both ways to make sure it looks like that. Now, if you want some quick test for symmetry, if the function has a sign in it, the main part of the function is a sign. it's probably going to be symmetric with respect to pi over 2. And if it graph has a cosine, it's probably with respect to the polar axis, the one we just did. Let's analyze another graph, 2 cosine 3 theta. Make a table for this graph, theta and r. Let's go at 0. I think this one, if I plug in pi over 3, it might actually work. But let's do let's do pi over 6, pi over 3, pi over 2. Then it'll be, the next one will be 2 pi over 3, 5 pi over 3, and then pi. Now, I'm going to try to do a lot of it on the top half, and I'm not going to do the back half because it's a cosine, so it should be symmetric about the 0 pole here, that line there. So I'm going to do a lot of the top ones and then see what happens. The first one, well, let's draw a unit circle. It's going to be 1, 0. Actually, before I do that, if I'm doing pi over 6 and pi over 3, I need to put the lines on here. So pi over 6 is close to the thing. Over here, it'll be pi over 6. 5 pi over 6 will be over here. That's pi over 3. And then same thing over here. That would be 2 pi over 3. So this is 0 and pi. That's 0, pi. We have pi over 6, pi over 3, pi over 2, 5 pi over 6, pi. Okay, so now we could go. So that's going to be 0, 1. That's going to be negative 1, 0. And that's going to be 0, negative 1. 0, pi over 2, pi, 3 pi over 2. And don't forget, cosine is the x value. At 0, we're going to get 2 cosine of 3 times 0, which is just equal to 2 cosine of 0, which is 1. At 0, we're going to be at 2, right there. Okay, next one. 5 pi over 6, pi over 6. 2 times cosine of 3 times pi over 6. Those cancel out and reduce, and you get 2 times cosine of pi over 2 is 0. This is just 0, you just get 0. Next one. 2 times cosine 3 times pi over 3. Those reduce, and you get 2 times cosine of pi, which is negative 1, so negative 2. So we have pi over 3. Got pi over 3, we're going to go negative 2. On this line here, we're going to go negative 2. So right now, my graph's kind of going like this. Next one, pi over 2. 2 times cosine of 3 times pi over 2, which just gets me 2 cosine of 3 pi over 2. 3 pi over 2 is down here. X is 0, so that's 0. Then we go back down to 0. So we have to click curve back again. Next one, 2 pi over 3. 2 times cosine of 3 times 2 pi over 3. Those cancel out. We just get 2 cosine of 2 pi. Cosine of 2 pi is the same thing as 0. So right there, go to 1. So it's just 2. Again, watch how we write this. At 2 pi over 3, which is this line here, we're going to go to 2. We're going to go up to 2 here. Like that. Okay. So my graph, if it keeps on going, it's going to this now. Next one's 5 pi over 6. So 2 times cosine of 3 times 5 pi over 6. Those reduce, and I get 2 times cosine of 5 pi over 2. So 5 pi over 2, we go back down to 0 again. And then one more, cosine of pi. 2 cosine of pi, 3 pi I should say. 3 times pi. 3 pi, so negative 1. So it's 2 times negative 1, so negative 2. But pi, this line here, we're going to go back to. This is the line we're going to go back to. 1, 2. So we go back to where we started. And we get this propeller, I call it. So that's a propeller graph. And that's how this one works. So I could have kept on going on, but it's going to be symmetric across this line. So it's going to be the exact same graph over and over again. That's another one of the polar graphs. Here's some special polar graphs. Several important types of graphs have equations that are simpler in polar form than they are rectangular form. For example, the circle. R equals sine theta is a circle. So much more simple than x squared plus y minus 2 squared equals 4. Another version of this is called limacons. These right here are much easier to draw in polar than they are to do in rectangular. It's a plus or minus b cosine theta, or a plus or minus b sine theta. It gets you more of a little curve there. So these are limacons. They're much easier to graph in polar than they are in rectangular. Same thing with the rose petals we just did. This will be really hard to draw in rectangular, but in polar it's actually fairly easy. It's just r equals a cosine n theta, where a is the length of the petal. So you can see here, a is always the length of the petal. And n, it depends. If n is odd, it's just the number of petals. Here we have 3, n is 3, we have 3 petals. Here n is 5, we have 5 petals. But when it's even, then it's 2n petals. Here we have n is 4, so we're going to have 8 petals. And here n is 2, we have 4 petals. When it's sine, it's symmetrical across pi over 2. When it's cosine, it's symmetrical across the pole here. That stuff's much easier to graph on polar than it is rectangular. And we also have circles. We talked about circles are much easier to graph in polar. Same concept. If you have cosine, it's symmetric about this pole here. If you have sine, it's going to be symmetric about pi over 2. And lemniscates are right here, as this is the formula for them. And then likewise, that's how it works. So this next one here, we're going to actually use our calculator to do it. Let's bring out our calculator. Then we're going to analyze this graph here. First, we got to put it in polar form. We'll go to mode, By default, we're generally in functions. We're going to go to polar, like that. And now when I hit y equals, you're going to see it's all r theta. We're going to plug in this 3 cosine of 2x. So it's going to be a theta because it's from polar. And close that. Now we should be in radians. I think we already are. And hit graph, and you get a petal like that. If I want to zoom in a little, I know it should only go 3 width here. I probably should go from -3 to 3. That's 0 to 2 pi basically. 0 to 2 pi is like a circle. So if I look at my graph, we're going from 0 all the way to 2 pi. When I hit my window, that's 2 pi. That's 3.14 times 2. X min, X max, let's go from -3 to 3. And the same thing with the Y min, minus. We'll go -3 to 3. You can really see it. Hit graph, and there we go. Because that's what this tells me, how wide my petal should be. And then we're going to double the number of petals there. We do. And that's what that graph looks like. If I wanted things like the x-intercepts, that would be here, 3, 0. That would be 0, 0. And -3, 0. This is in rectangular. If I wanted in polar, it would be pi. There's lots of choices, but pi and 3, 0 and 3, and so on. If you want the y-intercept based on rectangular, you'd go 0, 3, and the y-intercepts would be 0, 3, and then 0, -3. That's what that one looks like. It's a rose curve. Now let's look at a lemniscate. Now this one, when we go back to our y equals, these are all r's. This is r squared. We have to square root it. So that's what we put in our calculator. We'll square root both of them, and we get r equals square root of 9 sine of 2 theta. I'm going to type it into our calculator right here. Second square root, 9 sine 2 theta. Close it. Close our square root probably. Hit graph, and get our lemniscate. Look at graph that. So that's what that one looks like. You can see it's symmetric to the pole, and it has an x and y intercept at 0. Anyway, that's the lesson.